Question 15. Let's read. Which region of the electromagnetic spectrum includes waves with a frequency of 10 to the 7 power megahertz? First, we need to translate the megahertz into plain hertz. So how we do that? So we already have 10 to the 7, and mega is 10 to the 6. So and then you keep the base and add the exponents. So this wavelength that we are trying to figure out has a frequency of 10 to the 13 hertz. Then we have our selection: infrared waves, radio waves, ultraviolet waves, or X-rays. To answer this question, let's go back to our classroom notes. So this shows from radio waves to gamma rays in terms now of frequency. So just the exponents, all right? So that's the range. So let's say that goes from 10 up to 10 to the 18 hertz. Then we need to shop some sections here for frequency. So radio waves go up to 8, microwaves go up to 11, infrared go up to 14, visible light go up to 16, ultraviolet 17, X-rays up to 18, and maybe higher will be a little bit gamma rays that kind of blend together, but up to 18 is considered as gamma rays. So to find the frequency from this problem, which is 10 to 13 hertz, we need to look our table right here. So 10 to 13 is right here in this range, which corresponds to the infrared spectrum. Okay, so this is a summary of the EM waves spectrum from radio waves to gamma rays, and this is the frequency in numerical order just by power of 10 exponents. And so for radio, go from 1 to 8, micro 9, 11, infrared 12 to 14, visible light 15 to 16, ultraviolet 16 to 17. So notice that when get higher range of frequencies, kind of blend a little bit at the end, 16 with 16, 17 with 17, 18 with 18. You need to memorize this. Question 16. A pipe closed at one end has a loudspeaker at the open end. A stationary sound wave is formed in the air within the pipe and an antinode at the open end of the pipe. The length of this pipe is 0.85 meter. The speed of the sound in the air is 340 meters per second. Which frequency of sound from the loudspeaker will not produce a stationary wave? I know you're not gonna have time to do a diagram like I did here, but I'm using this diagram to explain how to solve this problem. So here we have the same pipe, same one, and what I did here is I create a antinode because is where we need to hear something, right? So I have an antinode. So I'm going to assume this is an air pipe. So the sound is going to travel, is going to hit the end of the pipe, and is going to bounce back. So that's a stationary wave form here. However, just 1/4 of the stationary wave. Then another possibility is that I have the same antinode here, but now I'm gonna have 2 antinodes, one here and one here. So you just need To draw this quicker, just remember that the obstacle, where the wave hits the obstacle, is the end of the pipe, is the water, is always a node, always a node. So, and then from here you can determine, okay, so if this is a quarter, so this is another quarter, so you just connect those two nodes. So right here, you just, between those two, you create one more node in the center. So now you have more waves traveling in the pipe. And the last one that I did is the same thing. We start here, we have an antinode here, it's getting the quarter of a wave getting shorter, of course. So now we have a node, a node, a node, and you just connect and make those bubbles type of diagram. Now, in the length of this pipe, we can fit here a quarter of a wavelength. So if this is a quarter of a wavelength, we're right here on antinode. So now we have 1/4, you have another quarter here, you have another quarter here. So we have 1, 2, 3 quarter of a wavelength fit in this pipe. Likewise, if this is my antinode, this is my antinode, so this is 1/4, another one, and another one. So I'm going to add them. So 1, 2, 3, 4, 5. 5/4 fits in this pipe. So the last one, you have 1, 2, 3, 4, 5, 6, 7. So 7/4 of a wavelength fits in this pipe. Now the wavelength in terms of the length is, you just do cross multiplication right here. So is lambda is 4L. This is lambda is 4L over 3. And this is 4L over 5. And this is 4L over 7. So these are the values of the wavelength in terms of the length of this pipe. Okay, so the problem provided the length of the pipe, and here are possible stationary waves formed in the pipe. Based on that, the opening section, we have an antinode, and the other end of the pipe, because it's closed, we are going to have a node. So based on that information, you can draw a sequence of stationary waves as long as you keep here the antinode and this the node. So what I did is, like I explained before, that I draw all these waves based on this information. Antinode, and the end of the pipe, because it's closed, is a node. Okay, so now I derive the what is the portion of a wavelength that fit in the pipe. So in this case here, we have just a quarter, a long one, all right? It's a quarter. A complete will be like this, keep going. This one here fits 3/4, so 1, 2, 3, and so on. So now I want to calculate in terms of the wavelength in terms in meter. So that way we need to find the relationship between wavelength and the length of the pipe that was given is 0.85 meter, 0.85 meter. Okay, so now what I did was I just did the substitution. 4 times 0.85 for every single one. So that is the length of a wavelength that will be a complete wavelength. Now here fits just 1/4, but this wavelength with a quarter this long will produce a wavelength of 3.4 meter, which is pretty long. And this one here will produce a complete wavelength of 0.48 meters, almost half of a meter. So it's like this will be like almost half of a meter, okay? So that's what's going on here. So then my next step is to determine the frequency for each situation. So I start with the wave formula, which is wavelength times the frequency, but what I want to focus on the frequency that will be produced in the pipe. And so V over the wavelength, the speed of sound in the air was provided in the problem, which is 340 meters per second for every single one. And now the wavelength is based on this. To have a whole number like I'm having here, you have to go back to the problem. For example, in this case, let's see in this case right here that we have decimals, right? So go back here, and what you are gonna do is do 4 divided by 3, right? 4/3 times 0.85, which is this, right? All the decimals, and use right here. I'm going to invert because it's on the denominator, times 340, and you have a whole number 300. So that's how I got all whole numbers, because I have saved in my calculator. I just wrote here to guide you about your answers, but I work with the number that was stored in my calculator. So that's why I have the beautiful results that I got here. Now back to the problem. Now that I have a sequence of frequencies that is producing this stationary wave inside this pipe, I'm looking for the one that will not be produced. So do I see 100 here? Yes, so that's not the one. Do I see 300? Yes. Do I see 500? Yes. Do I see 700? It's not here, because I kept going. If you keep going, you're gonna get higher and higher. So that was the highest one, so that's okay. But I don't see 200. So between 100 and that is nothing. That is the next one is 300. So 200 is the frequency that will not be produced in the pipe to make a stationary wave. A note about this problem. You take too long for you do all this on your test. But if you study right now with understanding what's going on in the pipe with the information that was given to you, you can easily spot the sequence that you need to take to answer this question and minimize the time that you are working on here.